Okay, so I'll start. Hello, everyone. So my name is Kevin, and today I'll teach you guys about this theory called graph theory. And this is starting with the graph theory. I'll just like to clarify that it's not the graph theory from combinatorics. It's the graph theory from what we like mostly known as like computing, like programming. And so graph theory is a non-linear data structures, and graph theory could be also defined as algorithms, which is a process by using many different rules doing calculations to solve a problem much efficiently and accurately. So before I talk about graphs, I would like to talk about like the difference between graphs and trees. I'm pretty sure if you guys have done computing before, then you guys would be aware of what graphs and what trees are. And also trees, they are another type of nonlinear data structures. And trees and graphs, they are very similarly structured, but they have one significant difference, and that is the cycle. A cycle is when a path starts from the given vertex and ends at the same vertex. And in most cases, or I'll just say in every single cases, graphs always have a cycle, while trees never have a cycle. So if we look at the figure on the right, the first one is a graph, while the second one is a tree. And for the graph, the cycle is from 0, 1, and 2. Since 2 goes back to 0, there's a cycle right there. So trees. Trees are nonlinear data structures without cycles, and family tree is a great example of trees in programming. The hierarchical structure is ordered in a way such that the child diverges to the parents, which diverges to the grandparents as well. And in trees, they contain nodes that are connected to each other by edges. So the nodes are like 1, here, 2, 3, while the edges are like the lines that connect from node to node, like right here. And nodes, it can contain either value or any other sort of information. And by using the same concept of trees, the first node, the most primary part, the first node right here, it is known as a primary node. And from the primary node, all of the following nodes are very significant in relation to the root. And the last node of a tree are known as the leaves because these special nodes, they do not have any children. And also, the height of the tree is known as the longest distance between the root and the leaf. So for example, in this tree, in the right, it will be from 1 through 2 to the 4 to the 8, so the height would be 3. And the height of a tree is useful in programming and other algorithms that extend trees like the lowest common ancestor. And now I would like to move on to graphs. And graphs, there are mainly 2 types of graphs here, and it could be solved in mainly two different ways. So the first way is the depth first search, or the DFS, while the second way is called the breadth first search, which is BFS. And if you guys have done coding before, then I'm pretty sure that you guys will be very familiar with these 2 topics here. And yes, they're both recursive functions with cycles. And people who are looking at the screen share right now, where are the cycles on the graph at the right side? Do anyone know? Where's the cycles? Yeah, 1, 2, 5 is 1, and the second one is 2, 3, 4, 5. So DFS. Depth first search is a recursive function, recursive algorithm for searching all the vertices of a graph or tree data structure. Even though like I spoke earlier that DFS is more like a graph, it could be also used in a tree as well, but it's mostly more well-known used in a graph, I say. And the algorithm, it could be implemented by using a recursive function where the graph, there's the vertex, which I'll call as a primary node. And then there are like the other nodes, and then it will be differentiated into two categories. It's the nodes that are visited and the nodes that are not visited. And since the purpose of the algorithm is to check like every single node once, a node that was visited, it obviously shouldn't be repeatedly visited again. And DFS, it has a primary objective of viewing the depth of the graph rather than the width. So if you look at this thing right here, it goes from A to B to D to H, and then it goes back to D to B, and then it goes back down to E and I. And yes, so what this means by is that the algorithm starts at the root node, an arbitrary node, and explores as far as possible along each branch before backtracking. And in here, the notion is to start from the root or any random node, mark the node as visited, move to the adjacent node unless it is already visited, and continue the loop until all of the nodes are visited. Then backtrack and check for other visited nodes and traverse them. Lastly, print the nodes in the path. So this is like an example problem solved by DFS. So the problem asks for the maximum number of nodes that a person is able to achieve when the person starts at node 1. The person is only allowed to move to the adjacent node. So you start from 1 here, and then you move to 2, to 3, and then you go back to 2 since it's the depth first search, and then from 2, you move to 5, and then from 5, you move to 6. And since all the adjacent nodes are over, we just count how many of them, and then the answer will be 5. And then this is the source code I have above, and just like quickly analyzing the code, I made like an array of adjacent, I guess, which shows that if they are equal to 1, then that shows that they are connected. And lastly, in the recursive function of the DFS, I have to check whether the node is connected or not visited in order to continue the DFS. Okay, now I'll move on to BFS, which is the breadth first search. It's the algorithm that is very similar to DFS, but there's one significant difference here again. Unlike DFS, BFS is a breadth first search. So the program takes a look at the width rather than the depth. Now when a node in the graph is determined, instead of going deep down the graph, the node takes a look onto all nodes that are adjacent to the original node first. And then the primary node will travel to the first adjacent node and repeat the following. And one special thing that BFS uses, unlike DFS, is that BFS uses queues, which is like another type of famous data structure. So queues, they are like type of data structure that operates in a FIFO context, which is like more known as first in, first out, where elements are inserted into one end of the data structure and extracted from the other. And in the BFS algorithm, there are 4 different methods of queues, which include push, which is inserting the data in, pop, which is deleting the data in, front, which is like printing the data at the most front, and empty, which is like a Boolean to check whether the queue is empty or not. And continuing with the algorithm, it is processed by the procedure here, which they start from the primary node, they push the node, and if there's another node that is connected, which is like the adjacent node and not visited, then visit the following node. So unlike DFS that went from A to B to D to H and then back up and back down, for this one, we just check like A to B to C because C is the next adjacent one, and then Now we check the ones that are adjacent to B, which is D and E, and then check the ones that are adjacent to C, which is F and G. And this makes BFS our comment much more efficient and quicker than the depth first search. And if we look at the example problem solved by BFS, this is the same problem I mentioned earlier. It's that this problem asks for like the maximum number of nodes. What I do here is same as the DFS, I connect the 2 points, I guess. And then from the BFS, I check whether the 2 is empty or not, and then keep on pushing it instead of like doing a recursive function of DFS, which makes the time elapsed to be like much shorter than the depth first search. Is there any questions? Yes, thank you.